Welcome back. So, we ended the last lecture with the introduction of p-n junction. I told you the definition of depletion region, how a depletion region is formed and why is it called depletion, how electrons and holes will diffuse from one side to another side and create the depletion region. Okay. I also mentioned repeatedly that there is a field that will develop in the depletion region. We will see in today's class how that fields will be operational and all, but the field will oppose any further movement of electrons from n side and holes from p side from diffusing to the other side. They will prevent it, the field will prevent it. So, today's lecture will focus on the energy band diagram of the p-n junction, okay, and we shall introduce a few concepts like built-in potential for example, and try to understand what defines the extent of depletion on the region, depletion region, how wide is that region, is it 5 nanometer, is it 500 nanometer, is it 5000 nanometer, whatever. How do you know how much depletion has formed and what is built-in potential? We will only focus on static condition, which means no voltage is applied, no light is shining, it's equilibrium. There is absolutely no electricity flowing through p-n junction. That's called p-n junction in equilibrium, and that's what we are studying till now. Okay, no voltage is applied. So, we'll come to the whiteboard now and we'll continue from where we had left last time. Okay. So, I told you that you have a p, you have an n. Because holes will try to diffuse from p side to n side, electrons will try to come from n side to p side, they will recombine near the junction and there is a depletion region that forms. The name depletion means that this region is depleted of carrier because electrons and holes have recombined. There are no mobile carriers here. What remains is negatively charged acceptor ions, positively charged donor ions. Of course, this region has lot of mobile holes and also ionized acceptors. This is called neutral region. This is also called neutral region. This is also called neutral region because there are very number of negatively charged electrons, but also equal number of positively charged donor ions. So, this region is called neutral region. This region is called also neutral region. There are no fields here. There will be no electric field in neutral region. Okay. No field in the neutral region. The field only exists in this region. There is a field only in the depletion region, only in depletion region. Okay. And the field prevents from further diffusion, I told you. So, how will actually the energy band diagram of this semiconductor look like, of this junction look like? Okay. So, you have a p-type semiconductor. So, suppose this is EC, this is valence band EV, and suppose the Fermi level, this is a p-type semiconductor, so Fermi level is here. Okay, this is your Fermi level. Okay. Now, this is your n-type semiconductor, conduction band, valence band, and this is a Fermi level. If you remember, these are all lightly doped semiconductors at room temperature, 100% ionized. So, there is no incomplete ionization. Now, these are before joining. This is p-type, this is n-type. Now, when we join, the thing that we should keep in mind in equilibrium, at equilibrium there will be no current flow, right. If there is no current flow, then Fermi level EF, okay, Fermi level will have to be constant throughout. If there is equilibrium and there is no net current flow, then Fermi level has to be constant throughout, because any slope in Fermi level, any gradient in Fermi level means it is not equilibrium, current is flowing. Okay. So, now basically what it means is that, what does it mean? It means that the Fermi level on this side has to basically become equal to the Fermi level on this side. In other words, this side will have to come up and this side will have to come slightly down, so that this Fermi level aligns with this Fermi level. So, I'll bring this up, I'll bring this down until the Fermi levels align, and that is equilibrium. So, eventually the Fermi level has to be same throughout. Eventually the Fermi level has to be same throughout. Okay. It has to be constant and same throughout. Suppose this was your junction that has formed. This was x equal to 0, where on the left side p type is there, on this side p type is there, on the right side you have n type, and they have joined here. So the Fermi level has become equal. So far away from the junction, if I go back to the previous slide, far away from the junction, this spacing of conduction band and Fermi level has to remain constant because the doping has not changed. Far away from the junction, this difference of Fermi level minus valence band, that dictates your p type concentration, by the way, this dictates your n type concentration, by the way, that cannot change because the doping has not changed. Only near the junction some spice is taking place, some event is occurring. Away from the junction, this should be preserved, this diagram should be preserved. Okay, so away from the junction, so far away from the junction, this is n side, right? So the far away from the junction, your conduction band and Fermi level have to have the same difference. This is valence band, and far away from the junction on the p side also, your valence band, this is your EV, and this is your conduction band EC, this is same. So you see this particular region and this particular region is the same before and after joining, but the Fermi level has now aligned. If you look carefully in the red colored EF, the Fermi level has aligned, right? So now what you do is you join this conduction band and valence band. So conduction band will now be joined like this. Sorry, it will join here. I am not very good at drawing here, but you see my point, right? So conduction band will like that. There is no discontinuity, it smooths. Okay, it's smooth. My drawing is a little bit this thing. Similarly, valence band will have this. It is smooth. There is no discontinuity here. Okay, it's smooth. So now that is good. So this is x equal to 0. Which is the depletion region? The depletion region is the region where there is a field, and field exists whenever conduction band or valence band, whenever they have a slope. Whenever they have a slope, it means there is a field. That field need not be externally applied. The field can be internal also, as in this case I have not applied any external field. The field exists internally without application of any external voltage. Any slope in conduction and valence band means that there is a field. Is there a slope here? No, there is no slope. Is there a slope here? Of course there is no slope. So this region is your neutral region that I had been talking about. Okay, there is no slope here, no slope here. This is your neutral region that I have been talking about. The slope exists in this region. If you look at this region carefully, there is a slope. The conduction band is bending. That means there is a field that is up to here at this point. Similarly, it starts sloping. There is a field here. Eventually, it is up to here. So of course, slope in conduction band and valence band is the same because your band gap is the same. Your band gap is everywhere same, no? So whatever slope you have here is also the same slope that you have in valence band. So the field experienced by electrons here and the holes here is the same basically. Okay, because there is a slope here, there is a field here, and the field exists only in the depletion region. So this region is your depletion region actually. Okay, that is your depletion region where there are no mobile carriers. Okay, you see the depletion region has a definite width, and that is this W. I call it W, that extends from here to up to here, this line to this line. This is your depletion width. So let me come to the next page. Again I will draw the same thing. Now I will keep drawing the conduction, this energy band diagram, because this is like a very important thing. So this is here, this is here. Suppose this was the x equal to 0 point, the junction has formed. There is a field here, there is a depletion is extending up to here, up to here. This is W, the total depletion. Some depletion is on the N side, some depletion is on the P side. Of course, these regions are neutral. Okay, there is no field here and everything is neutral there. This is also neutral region. Only here it is there is a field, right? So some depletion has extended to the N side, some depletion has extended to the P side. So whatever has extended to the P side, this part has your negatively charged ionized acceptors, and whatever you have depleted on the N side, you have positively charged donor ions. So essentially that is what has happened. This is a positively charged donor side and this is a negatively charged donor side. Further electrons from n side will be blocked by this field, and further holes from the p side will also be blocked by this field. So, the field will prevent the hole from diffusing to the n side and prevent the electron from diffusing to the p side, which means, and you know, the field induced and the field related current is always called the drift current. So, essentially the drift component of the current will precisely balance the diffusion component trying to go to the other side here. So, drift and diffusion will cancel each other and the total current is 0 here. Now, you might ask, how is the field, I mean, which direction is the field, how is it blocking, how do you know the field is not blocking or blocking, you know. So, again I will draw this band diagram because it's very easy to explain it a band diagram. So, this is the Fermi level, again this is the p type, here n type, p type, n type. So, let us focus on the depletion region, which is say from here to up to here. Okay, this is the depletion region, this is your W, of course this is your junction, for example x equal to 0. So, you know, this is of course this is flat, so there is no field here, I keep telling you. Okay, similarly there is a flat here, it is flat, it starts from here, flat starts from here, so there is no field here, the field only exists in the depletion region. Now, I told you that look at this conduction band, this is conduction band, right. So, look at this conduction band, if you think of it this as a cemented floor, and if you place a rolling ball here, which direction will it roll? It will roll this side, no. So, same thing, an electron here will basically try to move in this direction, which means the field is in this direction. Okay. If the field is in this direction, the force on electron will be in this direction because it is negatively charged. So, whatever electrons are here in the n type region, this is n type region, no, there are many electrons here, they try to diffuse to the other side, but the field is in this direction, which means these electrons that are trying to diffuse will be pushed back in this direction, right, they will be pushed back, which means they will not be able to go to surmount this barrier. Similarly, if the field is in this direction, then the force on holes also will be in this direction because positively charged. So, whatever holes are here, if they try to diffuse on the other side of n, you know, because it is lower concentration, the field is in this direction, so holes will be pushed back in this direction. So, holes also will not be able to actually go back to the other side, So, the drift that is happening in this depletion region, will exactly balance out the diffusion tendencies of electrons and holes from both sides, the diffusion component. Okay, and that is why there will be no current that will flow, no current will eventually flow, it is all in equilibrium. Okay, it is all in equilibrium. That is why the field, that is how you find out the field direction. You just think of this as a slope, as a cemented floor, put a ball here which it will go in this direction, which means exactly the electrons will also go in this direction, which means the field is in this direction. Okay, that is how you basically find out the direction of the field in any semiconductor, and a field will be only there when there is a slope in the conduction band or valence band. So, please keep that in mind, because the band gap is same everywhere, the slope is also same, but remember in certain semiconductor the band gap might keep changing with distance. Those are heterostructure sort of devices. If the band gap keep changing with distance, then the field on electron and hole might be also different. We will come to that in one of the far classes in the next, you know, sometime later. So, again I will draw this junction now. This is your Fermi level, this is your conduction band, this is your valence band, and this is the depletion that has formed. I told you this is suppose the 0, x equal to 0. So, the depletion has extended a little bit on the n side. I call this distance as x equal to Wn, that is Wn is the depletion on the n side, and on this side I call this point as x equal to minus Wp. So, depletion on the p side, it has extended to the other side, this x equal to 0. The total depletion is this that has formed, okay, and total depletion is of course equal to Wn plus Wp, both are positive quantities that I am taking. Okay. We want to know how much is the depletion with, what is the depletion on the n side, what is the depletion on the p side. Those are very important terms that will actually decide how the device performs. Okay, that will decide how the device performs. That is also intricately connected with something else. Again I will draw it. Suppose I have a Fermi level here, I will keep drawing this so that you know it becomes very familiar all the time. So, this band gap is same, I am doing a mistake here. You see, this is the conduction band here. If you look at the conduction band thing again carefully, you know, I will take green color here for example. This conduction band and this side of the conduction band, they have a difference here in the energy. This is called the built-in potential, built-in voltage or built-in potential, same thing. We designate it as QVBI. You see the conduction band on the both sides, and same thing with valence band, of course. It's the same thing, okay? It's exactly the same thing because it's the same band gap. You see that voltage that has built up because of that field, you know, that voltage is called built-in voltage. You cannot measure it, by the way. You can only estimate or calculate it. You cannot measure it because to measure you have to pass current or you have to apply voltage. The moment you apply voltage or pass current, this equilibrium will be distorted and you cannot measure this again, okay. This is called built-in voltage, and we shall try to find out what is the value of this built-in voltage and how is it important. Oh, this built-in voltage is very important in the devices, okay, extremely important. So, how do you find out the built-in voltage? Fermi level, keep drawing this conduction band, valence band. Let me again not write this down because you know that this is conduction band, this is valence band. So, this is your conduction band, and so this is a Fermi level and this is your conduction band on both sides. This gap, this is doping on n side is Nd, the doping on p side is Na, okay. This and you know Nd equal to N here because it is 100% ionized, this is equal to P here. You see this gap between conduction band and Fermi level, I will call that phi n, that is conduction band and Fermi level difference on the n side. This is n side, no, it is called phi n, I will call it phi n generally, and this value is nothing but kT by q. You remember Maxwell-Boltzmann approximation because this is not a high doping, ln of Nc by n electron concentration, which is Nd basically. N is only Nd here, no, same thing, okay. Similarly, this gap on the p side is phi p, this is essentially your the Fermi level minus the valence band on the p side, and that value is called is actually kT by q ln of Nv by p. Of course, instead of p I can write Na on the doping on the n side. Oh, by the way, if there is an electron concentration here of this side, you know, what is the minority hole here? That minority hole here, I will say P of n because on this side is Ni square by Nd. That is the minority hole and it is very small in quantity. This is P here, it is very high. Electrons on this side Np, this is minority electron on P side, will be Ni square by Na. This is a very small quantity, this is a very large quantity, right. So, I know this is phi p, I know this is phi n. Now, if you look carefully again, this energy difference is actually if you recall very closely, this value QVBI is actually equal to this whole value minus this value, okay. So, some value here which is say some unknown quantity x maybe minus this phi n, that is equal to QVBI, this is this, right. This value is actually equal to this minus this, all agree? Yeah. This value, by the way, this value x that I am putting here, if you come this side, you will see that this is this value actually. Of course, the band, you know, the blue curve here is constant everywhere, okay. So, this is actually x, this is your x, right. You look at the Fermi level, right, and this x is nothing but this whole thing which is the band gap minus phi n phi p, this the whole is the band gap. Now, this entire thing is the band gap, remember this is band gap, conduction band, this is valence band. So, this is the whole thing is band gap. So, this band gap minus this gap, this phi p, band gap minus phi p is actually your x, this unknown quantity x. So, QVBI is actually given by x, which is nothing but band gap minus phi p minus this phi n, this is your QVBI. Let me go to the next page again. So, QVBI is band gap minus phi p, that is the this phi p basically you recall is your this gap and phi n is your this gap in the neutral region, right. So, phi p minus phi n, e.g. the band gap of the semiconductor minus phi p is nothing but kT by q ln Nv by Na, remember from the last page, this is minus kT by q ln Nc by Nd. So I can write QVBI equal to Eg minus Kt by Q ln Nc times Nv. These are conduction band effective density of states that are provided in the question always, divided by Na into Nd. This Na is the p side doping, remember, and this Nd is the n side doping, remember that. Okay, so this is your equation for your built-in potential. Can we simplify it further? We can actually simplify it further. I'll tell you how. Okay, let's simplify it even further. You remember the intrinsic carrier concentration of a semiconductor Ni is given by Nc Nv square root exponential of the band gap by 2 kT. So if I take a square here, Ni square, it becomes Nc Nv exponential minus Eg by 2 kT. If I take a log here, ln of Ni square is equal to ln of Nc Nv plus log of exponential, which is minus this, that will be minus Eg by, this is actually not 2 kT, this is kT because there is a square term, kT, Nc Nv minus Eg by kT. Shall we do this? Shall we put this equation? So basically what it means is that ln of Nc Nv is equal to ln of Ni square plus Eg by kT. Remember this equation? We will put it in the equation that we saw here. Q VBI equal to Eg minus kT by Q log of Nc Nv plus, because it is a minus minus here, kT by Q log of Na Nd. So this quantity, okay, that quantity we know from a different equation there, right? You remember here, this is the equation, right? So I'll write this equation, the previous equation, and I'll put this equation there. Okay, what will happen then? So I'll say Q VBI, again let me write it, is equal to Eg minus kT by Q ln of Nc Nv plus kT by Q ln of Na Nd. And the second equation was that this ln of Nc Nv is equal to ln of Ni square plus Eg by kT. Okay, so I just need to put this into this okay. This quantity is here. So how do I do that? I'll write this again, QVBI equal to Eg minus kT by Q, ln of this is this, so ln of Ni square, right, minus kT by Q into Eg by kT. Of course this is kT by Q only, I mean there will be an extra Q there, so that of course cancels out here, okay, and then plus kT by Q ln Na Nd. This cancels out, so Q VBI, actually this will be VBI only because there is a Q already here. So VBI will be equal to kT by Q ln of Na doping on the n side, doping on the p side by Ni square. This is your expression for the built-in potential. Okay, the built-in potential that has formed in a PN junction. Remember, this is your Fermi level, this is a conduction band, this is a valence band. This built-in potential that has formed, Q VBI, is this actually. Okay, I mean I can remove the Q here, of course, that's the same thing. So it depends as kT by Q ln Na Nd by Ni square. So Na is the doping on the p side, Nd is the doping on the n side. So the product of the doping divided by Ni square, that log of that value times kT will give you the built-in voltage. So for example, let's take an example here. Okay, we'll take an example here. So suppose this is your Fermi level, this is a conduction band, Suppose this is n type doped 10 to the power 16 per centimeter cube. This is p type doped say 10 to the power 17 per centimeter cube. Then this built-in voltage will be given by Kt, which is 0.026 at room temperature, ln Na into Nd, which is 10 to the power 17 into 10 to the power 16, the doping, by Ni square. What is Ni? For silicon, if you remember, it's 1.5 into 10 to the power 10. So this is 2.25 square, will be 2.25 into 10 to the power 20. So this will be 0.026 log of 1 by 2.25 into 10 to the power, this is 33, 20, 13. So you can just take log of this 10 to the power 13 divided by 2.25. So if I use the calculator here, okay, I'm going to use the calculator and I'll quickly let you know what the value is. So for example, you can do a calculator math actually, but the exact value will be how much. So for example, I take 10 to the power 13, so 1, e to the power 13, so that will be 10 to the power 13. Okay, that will be 10 to the power 13 divided by 2.25 is equal to approximately 4.44 into 10 to the power 12. So log of that quantity, how much will the log of that quantity be? So ln of 4.44, okay, into 10 to the power 12. So that's into 10 to the power 12 will be equal to, this quantity will be equal to 29.12. So the built-in potential will be Kt, which is 0.026 into 29.12, that will be almost equal to how much? 0.757 volt. So you see, if you have a doping of 10 to the power 17 on one side, doping of 10 to the power 16 on one side, the built-in potential will be almost equal to 0.76 volt. So that is the voltage that is dropping across the P and N. There is a built-in field here, a built-in potential that is here, and this potential cannot be measured, but this can be calculated. So this built-in potential of 0.76 volt has dropped. You see, this depends on the product of ln Na Nd by Ni square. So if your doping on both sides increases, then this quantity also increases, no, product, and so the built-in potential also increases as your doping increases. If on the other hand, if you take a narrow bandgap semiconductor, your Ni will be very large, then your built-in potential will be very small. If you take a wide bandgap semiconductor, then if the bandgap is large, say you take gallium nitride for example, the bandgap is 3.4 eV, right? So your Ni will be very, very low, very, very low. If Ni is very low, then this your Kt by Q times this quantity, the built-in voltage will be large. So a built-in voltage will be large if your bandgap is also large. So a larger bandgap essentially corresponds to a larger built-in voltage, and a larger doping also corresponds to a larger built-in voltage. And built-in voltage is very intricately connected with this length of this depletion region. The length of this depletion region, or this width you can say, is very intricately connected to the built-in voltage. So if you recall actually the block diagram, so this is your p type n side. I told you the depletion extends on both sides little bit. This is say minus Wp, this is 0, this is Wn, so it has extended this side, extended this side. This is all negatively charged acceptor ions, this is all positively charged acceptor ions. The charge is neutral here, I told you, the charge is neutral here, I told you. The charge also has to be neutral in this. And for the charge to be neutral, the areal density of this and this has to be equal. So this is nothing but Na minus, so Na minus is equal to Na only, times this Wp. This is the actually the area under this, like the areal density. That has to be equal to this charge, which is Nd, the doping that you are doing of course, into Wn, this one, right. So you see NaWp must be equal to NdWn. The total charge on either side has to be same. This means that if doping on one side is higher than the other, the depletion on that side is lower. So suppose I am doping p type as 10 to the power 17 and n type as 10 to the power 16. The p type doping is 10 times higher than n type doping, which means Wp has to be 10 times lower than Wn. Only then the product will be same, no? If Wp is suppose 100 nanometer, then 10 to the power 17 per centimeter cube into 100 nanometer will be equal to 10 to the power 16 per centimeter cube into 1000 nanometer. So then this will be 10 times larger. So basically they are in the inverse ratio. If the doping is high, then the depletion on that side is low. If the doping is low, 10 to the power 16, the depletion on that side is high. Only then the product will be same, no? Which means if I take for example NaWp equal to NdWn, if I take this as very high doping, say 10 to the power 18, and suppose this is very low doping, say 10 to the power 15, this is 1000 times lower doping than this, which means this will be 1000 times lower than this. So if this quantity is say 1000 nanometer, then this quantity Wp will be only 1 nanometer, which means in a realistic diagram when you draw, this is P, this is N, you know, this will be almost negligible, only 1 nanometer. On the other hand, this will be 1000 nanometer. So total depletion width will be Wn plus Wp is equal to W. 1 nanometer plus 1000 nanometer is equal to 1001 nanometer, which is almost the same as 1000. What I am trying to say is that doping on one side is extremely high compared to the doping on the other side, then the entire depletion region extends to the region where the doping is low. Okay, the depletion on the doping and the region where the doping is high can be neglected when the doping ratio is very high. Okay, so to re-emphasize and reiterate, you know, if I have a PN junction and this is dope very high, say 10 to the power 18, this is dope very low, say 10 to the power 15, then I can say that depletion is all the depletion is almost entirely in this side. There is negligible depletion on this side, because the depletion ratio is in inverse proportion to the doping. So this is 1000 times more than this, which means this is 1000 times lower thickness than this. So all the depletion actually is on the N side. Okay, this kind of junction is called P plus N. P plus is very highly doped, N is N, or if it is reverse, N is very highly doped, then you call it N plus P junction. Okay, then you will call it N as N plus P junction. Okay, so we will end the lecture here today. Okay, so we have finished up the derivation of PN junction built-in voltage. We have discussed the depletion width, how the depletion width actually splits in the ratio, the inverse ratio of the doping, and how the depletion, how the built-in potential actually is proportional to the doping concentration, the product of them, the band gap, because Ni square also comes in there. So these things we have discussed. The field, how the field opposes, the band diagram we have drawn many times. So now hopefully you are aware of how the band diagram looks like. This is all assuming room temperature, 100% ionization of carriers, okay, and it's moderate doping. So there's no jurisdiction sort of thing here. And finally, now in the next class we will discuss about the relation between the depletion region and the built-in voltage. For that we will have to solve the Poisson equation. Okay, that we will do in the next class. So thank you for your time, and we will continue on the next class. Okay.